Hello and welcome to SciLux, the podcast where we talk about scientific developments and technological changes in Luxembourg, as usual, proudly powered by Research Luxembourg and recording at the Media Center of the University of Luxembourg. And today we have two guests in our show and one connecting a little bit from afar, we could say, even from Chicago. So we have Emanuele Penocchio, who was trained as a chemist in Bologna and Pisa. He then joined the group Complex Systems and Statistical Mechanics, led by Professor Massimiliano Esposito. Currently, he works as postdoctoral researcher in the Gingrich Group at Northwestern University in Chicago. And Massimiliano Esposito, who is professor of theoretical physics at the University of Luxembourg. Massimiliano's research group specializes in non-equilibrium statistical physics and thermodynamics. Thank you very much for coming.
Thank you for inviting us.
Thank you for hosting.
The reason you're here is actually a very old reason. Almost a year ago or so, I met the two of you when Emanuele got a prize from Rolf Tarach, the best PhD thesis prize, I remember. Then you got another prize, and there are quite a few different prizes. So I said, okay, yes, before you get another prize, maybe let's talk and let's meet and figure it all out. Because honestly, I've checked quite a lot of stuff of what you're doing. And I have to say that it took me quite some time to understand it all. And I'm still not there. So I hope that after our today's meeting, I will be a bit closer to understanding.
Okay, we'll try our best.
Yeah, the problem is it's a podcast. And I know that you, Emanuele, you like also showing things. And of course, our listeners will not be able to see all your amazing steam machines or whatever else you've been showing. I also, for those who are interested, I've seen some videos from some science fairs in Italy as well, where you're showing different things. Yes, I can see you're rolling your eyes. So maybe I should not be mentioning that. I don't know. It was quite some time ago, I guess, right?
Yeah, I mean, the first one you can find on YouTube, I think, is when I was 20 years old. And of course, now I'm ashamed.
No, it's brilliant. And I wanted to ask you actually first thing, why did you want to explain to people what you're doing? I mean, come on, scientists, you just do the research. You don't go to the general public. You don't explain what you're doing that often as you did.
For me, there was a personal reason and let's say a political reason, if you can call it like that. So the personal reason was that I came from a family that basically couldn't afford paying my university. So let's say to go to the university, I always had to win some scholarships when I was the undergrad and the master. And so I always felt that I was receiving money from the state, from Italy in this case. And somehow I wanted to give back something to the society, immediately, let's say. So I had this push of sharing what I was learning as a way also maybe to show that I was learning something, I don't know. And this was kind of the personal reason. And if you want, the political reason is that science is something that we are developing, and I think that it should be open and accessible to everyone, even to people that do not have the means to go to university or to study. And so I have always thought that it's a good thing to try sharing science to the public.
That's a great point, Massimiliano, right?
Yeah.
But I think sharing science when it's theoretical physics is not very easy, is it?
No, of course, we cannot share really the details, but I think trying to convey the meaning of what we do is important because, as you say, for theoretical science, very often it's something that people have a hard time imagining. And so, finding ways to explain why what we do has meaning is important, and we always try it. I don't know if it works. My parents, I'm not sure, are fully convinced, but
This is actually one of the side kind of effects of this podcast. I noticed I had some of my guests saying, oh, my family finally understands what I do. So let's hope that maybe we will be able to explain that. And of course, let's get down to the business. So first of all, I noticed, Emanuele, when I Googled your name, sometimes it said you're a chemist. Sometimes it said you're a chemical physicist or physical chemist. So what is it actually?
I mean, I don't know neither. Jokes apart. So I started with chemistry. So I'm a chemist by background. And at the beginning, I even wanted to become an experimental chemist at some point. But then as soon as I started learning about theory, I realized that the questions I was more interested in were theoretical kind of questions. So I switched my interest more towards this discipline that is called physical chemistry. That is basically the intersection between physics and chemistry. Is basically trying to answer chemical questions with physics tool. And then for the PhD, I joined Massimiliano's group to learn about physics. So let's say if I have to pick a definition, I would say that I'm a physical chemist because I'm using physics to explain chemistry, but my object of study is chemistry.
And when Emanuele joined your group, did you understand him as a physical chemist, or it took you some time to kind of grasp the chemistry part of what he was trying to explain to you?
No, so interestingly, I often say that, I started studying chemistry too because I was hesitating between physics and biology. So I kind of picked the thing in between. And similarly, I very quickly realized that physics was the thing that was interesting me the most. And so I did all my academic research career in physics, in theoretical physics. But I was also interested in chemistry and in developing the concept from non-equilibrium thermodynamics in the context of chemistry. And so when Emanuele applied, I thought this was interesting to have a person with a real chemistry background that was interested in learning the tools that we were developing in the group to use them to explain how these molecular motors that have been synthesized in supramolecular chemistry could be analyzed and understood using what we were developing. So I thought this was an interesting opportunity. And it's always the best thing when from both sides there's something to be learned.
Yeah, so you already mentioned something, of course, I wanted to ask. So the non-equilibrium part, right? And you also, actually, it's not only non-equilibrium, it's non-equilibrium statistical physics altogether, right? Oh my God. So please tell me, what do you mean with that? And I guess it was appealing enough for Emanuele to join. So,
in a sense, to put it in an historical way, which is probably the more meaningful way to explain this, there's first thermodynamics, then there's equilibrium statistical mechanics, and then there's non-equilibrium statistical mechanics or statistical physics. Both are used similarly.
So this means that quantum physics and quantum mechanics is the same thing or not? Sorry.
Yeah, to a large extent, yes.
Okay, good.
Yes.
Anyway, we're not talking quantum today, fortunately, but it's coming. By the way, I wanted to tease all the listeners. We will be discussing quantum physics. I first have to read like 20,000 books and then there's going to be an episode about that. But coming back, so you said first thermodynamics.
Yes, first thermodynamics because it's the oldest science. It's a science that was developed to understand how thermal machine works. So we all know that a key step in human evolution has been the invention of machines, of heat engines. It played a key role. It has really transformed human society because the amount of energy that humans could mobilize changed by orders of magnitude. And it's because we started using the fossil energies that had been stored over millions of years by this solar energy that we could now release and use for our purpose. But the early questions were, okay, they started using these heat machines to pump water out of mines. And it was requiring humongous amounts of wood. And the obvious first question was, well, we don't want to burn that much wood, so how can we improve the performance and pump more with less wood? And that's this notion of efficiency, how efficient a machine is. And thermodynamics was really developed as a tool to understand how to improve the performance of these machines. But these machines were large machines, bulky machines. And so typically they operate not too far away from equilibrium. And so now we go to the notion of equilibrium that I should also explain. So equilibrium is really the state of matter where nothing happens because every process is balanced by its opposite process so that there are no net processes happening. So, you have a lot of thermal noise at small scales. So things always move, but there's no net motion because the probability to move in one direction is equal to the probability of moving in the opposite direction. So this is equilibrium, and thermodynamics was first developed as a theory describing systems at equilibrium. Then, of course, the problem is that you want to also be able to describe system out of equilibrium because the machine, when you operate at high power output, it is becoming further and further away from equilibrium. And in the molecular motors that Emanuele studied, the systems are very far from equilibrium. So there's really a need to extend the theory beyond equilibrium. That's when non-equilibrium thermodynamics enters, because we need to extend the theory to non-equilibrium. Thermodynamics, I should also say, it's a macroscopic theory. So as I said, this was meant to describe macroscopic machines. The key step, and this is now entering the explanation of what statistical mechanics or statistical physics is, was to understand how these laws of macroscopic thermodynamics, and maybe to give a simple example, it's the law of perfect gases, PV equal nRT, that is everybody learns in high school. This is an equation that is typical of equilibrium thermodynamics. It relates macroscopic properties describing a gas, temperature, pressure, volume, but it doesn't tell anything about the microscopic detail of the machine. And so a key step, conceptual, that was pioneered by Maxwell and Boltzmann, was to show that one can explain how the laws of thermodynamics emerge by postulating the existence of atoms and molecules and describing the behavior of these atoms and molecules in a statistical way. So that with probability theory, and assuming the existence of atom, which at that time was not even confirmed, one can basically show that these laws of thermodynamics emerge as a statistical theory, namely, it's the most likely behavior that is going to produce the laws of thermodynamics. And it was first done at equilibrium, but then it had to be extended to non-equilibrium. And most of the early theories were restricted to close to equilibrium systems. But the last 25 years by now witnessed the development of non-equilibrium statistical physics, which we often call stochastic thermodynamics, that can describe systems very far away from equilibrium. And this was basically discovered by trying to generalize thermodynamics to, instead of describe these macroscopic large machines, to study small machines that operate really at the nanoscale, at the molecular level, where thermal fluctuations play a very important role, and where, because the systems are so tiny, it's very easy to drive them very far away from equilibrium. The idea is that a bulky system, if you try to put a gradient of temperature on a bulky system, inside the bulk, the gradients will never be very large. But if you have a very small, tiny system, you can drive it very far away from equilibrium because there are no bulk property that are diluting those gradients. And so there it's really necessary to develop a theory that is valid far from equilibrium and in presence of thermal fluctuations that are very significant.
Okay, this is fascinating, and I think that's when we could move to the molecular motors and see how it applies. But before we do that, I actually have a request to both of you, because in the beginning of the podcast, we always have this moment to ask a pub quiz question. You both had such great ideas that I would like to use both, if possible. But first, we talked a bit thermodynamics. So, Emanuele, if you could ask your question about thermodynamics and one of the laws, and then we will move on to Massimiliano's question. That is also very, very interesting. And listeners, remember the answer only at the end of the podcast, so you need to listen to the whole thing to get it. Okay, Emanuele, can you ask the question, please?
Yeah. So my question is very simple, but has big implications. So the question is, can the second law of thermodynamics be violated?
Question is great, but actually I assume that some of the listeners went to school a long time ago and they might not remember what is the second law of thermodynamics. So if you can remind us that as well, that would be great.
Yeah. The problem is that the precise statement of the second law of thermodynamics requires one to remember what entropy is. So one possible statement is that the entropy of an isolated system can only grow. Sometimes entropy is associated with disorders or things that get messed up and up, but maybe an alternative statement is that can you create energy for free? This can be another possible statement, I think.
Or maybe can one extract work from a single heat reservoir? That would be the Kelvin. There are different formulations of
but
the
that's
second
the thing.
law.
That was what I was thinking. Like, I could see it in Emanuele's eyes. It's like, really? Because, this is one of the problems, right? When you go to school, you have to have it simplified, right? And it all seems so nice. And I was also thinking, like, I remember physics, and nobody told me that there were some non-equilibrium states, and everything seemed so easy, right? And then you actually, you forgot about that part that is actually applicable to so many different things.
But even nowadays at university, most of what we teach is at equilibrium. There's little about non-equilibrium. And the problem with the second law, as I said, thermodynamics was this phenomenological theory. And so people came up with different formulations, and it took time to understand that this was one single theory. And at the end, many of the formulations of the second law are manifestations of fundamental principles that are best described with mathematics. And that's why when one needs to say, okay, what is the second law in an appealing way, it always poses some questions. And if one wants to avoid the concept of entropy, I think that the best formulation is to say, can one extract work from an object that is in contact with a single heat reservoir? And the second law would say no in the traditional formulation. But then the puzzle is that if there are caveats and exceptions to that.
Okay, don't hint, because that already gives us an idea that probably there is something going on. But we have also another question. So what was your pop quiz question for our listeners, Massimiliano?
Yeah, so my question is whether the power per unit kilogram or per unit mass of the sun is higher than the power per unit mass of a human person.
Great. So we have two different directions. We will be discussing it all later on. I already am very much looking forward to the results. But now, as I hinted, we come back to the molecular motors. So we are at the non-equilibrium state, and we're looking very much deep at nanoscale, I guess. And what are we looking at actually, Emanuele? What is the thing that you're studying, and what do you know right now?
Yeah, so as Massimiliano said, thermodynamics developed as a science to study machines. So these macroscopic objects that we use to convert energy into some function. And the same concept can be applied also to very small molecular systems. So systems made out of molecules that in the same way they can convert energy in some form to some kind of function. In general, these are called chemical engines. And when the function is motion, so transporting something from one side to the other of a cell, for example, they are called molecular motors. Biology has a lot of examples of this kind of molecular systems, but also chemists right now are starting to synthesize in the lab examples of molecular engines and motors.
So this means that we already have observed enough to actually be able to create something synthetically.
Yes, and also the other way around. So the things that we observe in biology are so complicated that are very difficult to study. So by trying to reproduce the same principles in the lab, so by trying to realize a motor with simpler molecules, it's easier to study the fundamental principles of this kind of systems.
But you're never 100% sure then. You're just trying to be very close.
If your question is how one can drive motion at the nanoscale with molecules, this is a fundamental question that can be understood even with simple systems. So, for example, even a machine, complicated vehicles, if you ask the question how this vehicle can move, how it can convert energy into motion, you can actually showcase the principle with simpler experiments.
So does it mean that the theories that we so far have are 100% applicable, or there is a holy grail that you're looking for a new theory to apply to molecular motors or chemical engines?
All the theories are applicable within their assumptions. So I would say that for now, the theory that we have is actually more valid for synthetic systems because they are simpler. They match the assumptions of the theory more. While biological systems can be studied with the theory, I would say, but they work in the cell in a very complicated environment. They interact with a lot of other stuff. We don't exactly know many of the details about what's going on in a cell. So applying the theory to them to extract numbers, so to be quantitative, I would say is a bit harder than doing the same thing for synthetic systems. And that's why I focused on them in my thesis. But I would say that the theory is being developed without specifying its application. So the theory is kind of general. It has some assumptions. We are trying to relax a lot of these assumptions to have a more and more general theory. And right now, I think that these assumptions are well matched by synthetic systems.
Of course, I'm trying to imagine your work on a daily basis. And how do you actually observe even those synthetic chemical engines? I mean, what is it? You get a microscope and you watch them? I don't know. You just calculate certain behaviors. Can you see this with your bare eye? Probably not. It's nanoscale, right?
Yeah, no, it's not on the scale of the microscope. So I'm a theoretician, so I basically, I never see them and I don't do experiments. But I have a lot of collaborations with experimental groups that are studying this kind of thing. So actually, the molecules that they are dealing with are very simple organic molecules. So for example, I think that if you ever search on Wikipedia for some drugs, for example, the aspirin, you see these images of organic molecules. So those are the size of molecules that they are using. So these very simple organic molecules that are built in a smart way, such that in the presence of energy, that can be light or some chemicals that are at very high concentration, they can actually move in a preferred direction. And this is striking, because you are basically controlling the movement of an object that is super, super small, is basically at the nanoscale. And the way in which, chemists are very smart at synthesizing this kind of molecule and at extracting data on them. There are various experimental techniques, for example, a technique that it is used a lot to infer information on this kind of system is the nuclear magnetic resonance spectroscopy. So the same thing you would do in an hospital, you can also do it for molecules and extract information about their structure, their concentration. You can measure the rate at which the concentration change, and this provide you some information that you can use then to inform your theoretical models that then you can use to apply the theory, basically.
And this is an interesting point as well. As usual, we often discuss here in SciLax about the cooperation between scientists and how important it is that science is not done by one person, but there is a big group. So I assume that, when you do theoretical physics, you can't just do it on your own. You really need those experiments there to check your theories or not.
Yeah, I think it always goes both ways. There's a constant dialogue between theory and experiment. And experimentalists need theory to understand sometimes what they see, and theoretician needs experiments to know whether their theories are correct or not. And so there's this constant ongoing dialogue. But maybe on the question of observing, because it's an interesting question. I mean, it's not so long ago that we really started observing atoms and molecules thanks to certain techniques like scanning, tunneling, microscopy. So in certain cases, one can really watch directly atoms and molecules. But this, I think, if I remember well, it first came around 25 years ago. But it doesn't mean that we didn't have indirect ways of studying atoms and molecules. And a lot of, very often, science is like that. We study objects without having an immediate visual relation to the objects, but via observables, quantities that allow us to learn more about what is really going on. But one needs to kind of reconstruct a picture of what is really going on based on these different quantities that are measured.
And, Emanuele we focused on the molecular motors and everything around that. But you, Massimiliano, you look kind of more general, right? And thermodynamics and biology and biological systems as such. So how do you actually apply it all? I still want to get a bit more in depth, let's say. So I don't know, do you choose one part? Because here we have just one PhD student who comes to you, okay, I'm interested in that, I'm a chemist, I want to do that. Okay, but like, how do you get the whole theory around it? Do you also focus on something? Because, biological systems, that's everything.
I'm really on the very theoretical side of things. I'm not a modeler. So the way it works for me is that I read the theories that have been already established, and I try to think of contexts where this theory would not work and what would be required for this theory to work. Yeah, I started really at the very small scale because my PhD was about quantum systems interacting with thermal reservoirs. And there was I realized that there were questions that I could not answer with the existing theories. And of course, it's also not only a personal endeavor because I was not the only one and there were other people asking similar questions. And then, everybody adds new elements of comprehension and realizes that there's extension of the existing theory need to be formulated. And very often one does things without, at the beginning, really understanding the implications. But then certain experiments are done and certain things are validated, other are disproved. And so one needs to further push. And then it's a complex process to describe. The evolution of science is not something easy to explain. There's not an algorithm describing scientific progress. It's a complex back and forth, but it's mostly curiosity driven. And, when there are things that I don't understand, I try to understand them and I try to read what has been done and what is still open. And I ask myself whether, based on what I know, I could come with answers that other people did not think about. So that's the process. And maybe to go back to you were saying biology, how did I come to that? So I started with these small quantum systems. Then I felt that this was pretty well understood. And in a sense, because I knew about chemistry, I thought that maybe we could apply this concept to study chemistry. And since chemistry is very close to biology, and since thermodynamics, as we said, is about quantifying the performance of machines, metabolism is basically the biological machine. It's the chemistry that extracts energy from nutrients that have high energy value and extracts energy from it in order to power our own activity and the survival of the living systems. And so I thought that the concept that I had learned by studying this small system could be extended to study these metabolic networks. And that's how I started getting interested in that and pushing it further.
And how do the biologists react to that when the physicist says now I'll tell you how it all works?
We have different languages. So very often there's the need to find a common language to understand each other. And I think there's always a need to have a certain humility because I think, the biologists have a lot of experience and a lot of knowledge that is usually empirical. So they don't really know the range of validity of what they observe, but they know a lot. And so often it's interesting for me to carefully listen to what they have to say, but then also to formalize it. This is where our work comes in, is to provide a mathematical framework to express these things in a rigorous way. And to then see also what are the assumptions under which those statements hold or not. But often in the process, we simplify. So we can make precise statements, but assuming certain simplifications. And this, of course, sometimes biologists have a hard time accepting because they care about those details. And so it's a back and forth dialogue to see what we can really neglect and what we really need to keep. And hopefully it converges to a real collaboration. And I think in that regard, Emanuele was very successful because that's really what he did. He managed to bridge between my level of theory and the experimental side of things that was developed in Manchester to understand these molecular motors.
Are we talking about the experiment done by David Lee in 2016?
Yeah, I think Massi was referring to it.
So what was it about? What was the bridge then?
So they did this wonderful experiment that was basically, so it was the first time that we had like a synthetic molecular motor that was working the same way as biological one. So just an historical parenthesis. So in our cells, as I was saying before, we have plenty of molecular motors. So the most famous one is probably the one called kinesin. It's basically a protein that can walk along some microtubule, some structure in the cell, and our cells use this molecule to transport cargoes from one side to the other of the cell. So again, we have this direction movement at the nanoscale, and the energy that the cell uses to power these motors is chemical energy. So you might have heard about ATP, that is typically referred to as the energy currency of the cell. So the cell burns ATP, that is a molecule. It consumes a molecule to power this motor. In particular, this motor can catalyze the conversion, the composition of ATP. And by doing this catalysis, it can extract some energy that it can convert into motion. For a long time, chemists were not able to do that. They were only able to power synthetic motors by using light. So there was a Nobel Prize given in 2016 for a discovery made in 1999 about the first molecular motor that was driven by light. So what David Lee did in 2016 was synthesizing the first molecular motors, synthetic molecular motors, powered by some chemicals. So in the same way as kinesin is powered by ATP, this motor was powered by a molecule, not by light. So this was like a very important experiment, because it was the first time that we had a simple system that was working the same way as biological systems. So this was the experiment that we studied together with David Lee, because once they had this experiment, they were interested to model it with theory to understand both how to improve the motor, so optimization kind of questions, but also to understand thermodynamics questions, like how efficient is this motor, how the energy is used, so how does it work? So they were genuinely interested in this kind of questions, and they came to us. Actually, they wrote an email to the day of my birthday, so I had this birthday present of this collaboration. That was amazing. So now is basically 4 years that we constantly collaborate, and today, for example, they published another paper in Nature Synthesis about another systems, and I helped them in something. So it has been great. And yeah, so the experiment was about this, so chemically driven, let's say, molecular motor, and our collaboration was about understanding the thermodynamics of this system, thanks to the theory that Massi developed. As I was saying before, this is a very simple system, so it's not a protein in a cell that is interacting with a lot of other things that are produced in the cell in a very compact environment. This is like a system in a solvent, and you know perfectly what are the molecules in your solvent. You can measure them. The reactions are all well characterized. We know almost everything about these systems, I would say.
And do you know how much energy is needed to be introduced for it to work?
Yeah. We even computed the efficiency of this motor that was super low. So the efficiency was of the order of 10 to the minus 5. So very low compared to the efficiency of biological systems. And this tells you the difference between a system made by chemists with simple molecules in a solvent, and a system that is doing the same thing, but has been optimized by evolution over geological eras almost. And yeah, it's fascinating to see the difference in how these two systems work, and especially in how these two systems are efficient in what they do. And you really understand why biology is so complicated, because in order to optimize a system, you really need to go complex and have all this structure that helps you using the energy at best.
Okay, that's a fascinating story, by the way. The email that comes on birthday, imported collaboration. Okay, we're wrapping up a little bit slowly, but before we actually solve the pub quiz questions and we have a bit of a discussion still about the second law of thermodynamics and everything else, I wanted to ask you, Massimiliano, last question about ERC, of course, because, in Luxembourg, we like talking about it. There's once in a while somebody gets an ERC grant and then everybody is reminded of all the ERC grants before and there's a discussion again, whatever. So you've been lucky enough to get a consolidator grant some time ago. And I just wanted to ask you, how has the experience been and just a bit of, thoughts about how has the process been of getting an ERC grant for you?
Before that, I had an attract.
Yes, true, of course.
Grant. So in a sense, I was quite lucky because the attract grant is is also like an ERC.
And we should say FNR attract grant for
FNR
those who don't know. Yes.
And the very nice thing about those grants is that it's a 5-year term. So this is longer term than most grants, which are 3 years. It's also more significant, so one can have more ambitious projects. And it leaves quite a lot of freedom too. So this is also very precious to do good science because with an horizon of 5 years and significant freedom in how to use the money, it really allows to go for ambitious questions. So I think I was really lucky to have first the attract and then the ERC in a row. So this was like 10 years in a row of good funding. I think it allowed me to build a group of really excellent people. And I think we were successful to a large extent thanks to that. So I think these are very, very important grants. It's a good model to follow, to have these kinds of grants instead of very small ones for which one needs to apply more because, if you need to apply for one postdoc at a time or one PhD at a time, it's much more work. There, it's a big vision over 5 years. So that was really great.
But also a bit challenging, right? Because here we're talking really, for theoretical physics. I mean, how can you promise solutions in 5 years? I think that's a little bit tricky,
The thing is that you cannot predict research. This is kind of an illusion. We all have to pretend to a certain extent that we know what we're going to do, but we actually don't really know. It's simply that there are some good ideas and then, you have to test them and see if something comes out of it. And the truth is that you can spend months writing a grant with a key idea, and it takes you a week to realize that it's wrong and that you need to move to something completely different. I know that funders do not like that. This is an intrinsic problem in funding basic research. The thing is to show that one is capable of doing things, that in the past one has done things, that one has good ideas for the future. And this is why ERC is a very good funding scheme, because once one gets that money, and it's very selective to get there, one needs to show past achievements and demonstrate that one has good visions for the future that are timely and that are things that have not yet been done. But then it's basically, okay, you prove that and we trust you that you can do a meaningful thing with that money over 5 years. I think that's very important, and that's really how research works. Basic research requires this freedom of inquiry and testing ideas, and some fail and new ones come. And very often after a few years, one realizes that what one is doing now has very little to do with what one thought one would do 3 years before. So it's important to keep that in mind. And I think, it's also for funding agencies something important to keep in mind also.
Yeah, that's a good appeal, I think, and a nice way to finish off the discussion. But the last thing, as I promised, we're coming back to the pub quiz questions, right? So, Emanuele, can you remind us what the question was without giving the second law of thermodynamics, and then give us the answer?
Yeah, the question was if the second law of thermodynamics can be violated, which means, for example, can you extract energy for free? So from an object that is in equilibrium, can you extract energy from it.
And the answer is?
The answer is that, surprisingly, when you look at objects that are very, very small, yes, the second law can be violated sometimes. The technical word is in single trajectories. If I can make an example, so in the macroscopic world, we kind of see a direction of time, let's say, no? So if I have a glass and I throw it on the ground, it breaks, and this process is kind of irreversible. So nobody would think that the glass can spontaneously reconstruct itself after it broke. Actually, at the nanoscale, you can see events that are similar to that. So at the nanoscale, you can see events that are as surprising as the spontaneous reconstruction of a broken glass. And the reason is that now we understand that the probability of an event to happen is proportional, actually is exponentially proportional to the energetics involved in that event. So for macroscopic objects like a glass, it takes you a lot of energy to reconstruct the glass. So the probability that would happen is very low, and basically we will never observe that in our lifetime or in the lifetime of the universe. But when you go at the nanoscale, the energies that are at play there are very small. So sometimes you can observe things going spontaneously in what we would call the wrong direction from our macroscopic intuition. And so sometimes you can see violation of the second law. So energy that extract energy from the thermal environment and stuff like that. But then the point is that now we understand the second law a bit better. So we understand it in a statistical sense. So the bad news is that on average, what you would observe is still something that respects the second law, in the sense that on average, you cannot extract energy for free. You can do it sometimes, but if you want to do it systematically several times, you cannot do it, and the second law still holds.
So the important part is on average, right? I think in this case.
Is the statistical part of thermodynamics.
Let's go back to the other question we had. So, Massimiliano, what was the question and what is the answer?
So the question is whether the sun was producing more power per unit kilogram than a human person. And the answer is no, which may a priori be very counterintuitive. And it's actually a strong no, because the power per unit kilogram of the sun is about 10,000 times less than the power generated by a human. And this shows you that we are objects very far from equilibrium that generate a lot of energy. And maybe the most powerful objects in the universe in terms of, type of objects. The sun, usually one thinks of it as a humongous source of energy. It is humongous by its size, but in terms of density, it is much lower than us. And so I think this really shows how special we are, and also how, in order to describe a biological system, one really needs to go away from equilibrium, because a fundamental characteristics of biology is that a living system needs a continuous burning of energy to be maintained. And these amounts of burning of energies are humongous compared to most other objects in the universe.
Okay, so I would say that we could summarize our discussion here is that the lack of equilibrium is very good. That's my first summary. And the second thing is, like, we keep looking for energy, and it kind of is sometimes there, but on average, it's not there. Or in general, statistics comes into play, and energy is extremely important. And we as human beings are a brilliant source of energy. Whatever happens with it later on, that's a different story. Thank you so much for today. This was really fascinating. Thank you, Massimiliano and Emanuele.
Thank you.
Thank you.
And this is it for today. Don't forget to subscribe, to follow us, to write what you thought about this episode, other episodes, suggest guests, comment. We are present in all the social media, always open to talking with you about all your ideas you have about SciLux and the scientists here in Luxembourg and abroad, because Emanuele is not with us here anymore. This was SciLux, and my name is Hanna Siemaszko.